In the last video, we looked at the overall setup of a built-in self-test, and we took a deeper look at the automatic test pattern generator, and we looked at the specific case where ATPG is performed using a linear feedback shift register. We ended up with this kind of strange truth table, and this is a truth table where the inputs of the circuit under test are the outputs of the LFSR, or the linear feedback shift register. We looked at how the specific sequence of outputs from the LFSR can be obtained and how we can obtain these outputs from the circuit for each of these applied inputs. So the circuit under test is a very simple sum of products circuit where the output is AB plus CD. And so F, in this case, is going to be equal to AB plus CD. Now, the remaining columns of the truth table represent cases where there are faults within the circuit. So the first column is a case where the variable A is stuck at 0. So node A is stuck at 0. In that case, F for A stuck at 0 can be evaluated as the function F where the value of A is always 0, meaning that the first product term is irrelevant, and so the output is equal to CD. And so we can fill this column as the output CD. Similarly, we can do the same for cases where C is stuck at 1, because in that case, for example, F is going to be equal to AB plus D. We can do it for cases where B is stuck at 1. In that case, F is going to be equal to A plus CD. When F is stuck at 0, F is equal to 0. And we also identify internal signals X and Y, which are internal nodes within the CLB. And we can also estimate the output of the circuit for any of these cases. So for X stuck at 1, F is going to be equal to CD plus 1, which is going to be equal to 1. And so you can see that for all the columns here, the output is equal to 1. But when X is equal to 0, F is going to be equal to CD. And so you're going to see that this column is identical to this column because the outputs are identical in both cases and are equal to CD. So how do we know that there is a fault or that there isn't a fault, and how can we identify which fault has occurred? So we can know that there's a fault. We know for a fact that we can do this if we manually inspect the outputs by comparing the outputs that we observe with the gold standard. And the gold standard here in this case is the first column of the truth table. This is the output that you expect to see if the circuit is functioning properly. There's no difference here between what we do here and what we did in the video that covered the fault model, the stochastic fault model, except that the inputs are applied out of order, which means that F is also out of order. And so when you compare, you should compare to the out of order F and compare the faulty outputs also out of order. So that's the only difference. Again, why is having the inputs and the outputs being out of order good? Because the normal order of a truth table will take too long to switch the values of certain variables, which will reduce our fault coverage. So in any case, you do know that there's a fault when you see a discrepancy between the first column and the column that you are at. So for example, you can see that this is different in the A stuck at 0 column and the F column. You see that this is also different. So when you see cases where there's differences, this is a test vector that can uncover this fault. What you will see here is that for all of these faults, there is a test case early that uncovers the fault. And this is exactly what we want to see. We want to see most of the faults uncovered by an early application of inputs. And the reason that applying inputs out of order will do that is that some faults will require specific combos of variables to uncover them. For example, if A is stuck at 0, then you need to apply an input where A is equal to 1 in order to detect that the fault exists. If you had applied the normal truth table order, that would take half of the truth table before that input was applied. Of course, it doesn't make a lot of difference in this case because we are talking about a 4-input CLB, which means that the entire truth table is 16 lines long. But in practical circuits with a large number of inputs, it will make a huge difference. And so you can see that all of the faults in this case are actually uncovered in the first half of the truth table, maybe even earlier. And that means that this is a successful application of automatic test pattern generation. Now, the other part of built-in self-tests is what is marked as signature analyzer in this block diagram. A signature analyzer is just one way in which you can examine the outputs of the circuit in order to determine if it's working properly or not. It's just that a built-in self-test is not only supposed to apply the input vectors to the circuit under test, it's also supposed to make a decision about whether the circuit is working properly or not. So the simplest way in which it can do this is that it can compare the outputs to the gold standard and just give us feedback about yes or no, the circuit is working properly, we have a bit match, or no, the circuit isn't working properly and we don't have a bit match. What we have here though with the signature analyzer is a little bit more involved. So for this circuit, which has 4 inputs, the circuit under test has 4 inputs. So we did examine this part of the setup in the earlier video with the ATPG and the circuit under test. You can see here the remaining part, which is the signature analyzer, and it's just being fed the output of the circuit under test. So let's look at the output of the circuit under test, F. If this circuit under test has M inputs, then strictly speaking, we need to apply 2 to the power of M input patterns to the circuit to test it. And so we need to observe a stream of F, which is 2 to the power of M bits long. So again, with good test fault coverage, we don't need to observe the entire sequence of 2 to the power of M bits coming out of the CLB or the circuit under test. Instead, we observe a set T, which is smaller than 2 to the power of M, smaller than or equal. If we have a well-designed test, which is the case here, then we should have a much shorter sequence that we need to observe. So let's take another look at this specific case. Here we have 7 possible faults that could happen in the circuit, and we see in italics the cells where the output of the circuit with fault is different from the output of the non-faulty circuit. And so A stuck at 0 needs the application of 6 cycles before we uncover the fault, or 6 input patterns before we uncover the fault. X stuck at 1 is detected in cycle 1, X stuck at 0 is detected in cycle 6, C stuck at 1 is detected in cycle 5, and Y stuck at 0 is detected in cycle 8, F stuck at 0 is detected in cycle 6, and B stuck at 1 is detected in cycle 1. And so if these are the possible faults that can happen in the circuit, we don't actually need to apply 2 to the power of M inputs, which is equal to 16 in this case. No, instead we just need to apply a number of tests T, which is equal to 8, because the last fault to be uncovered is the fault Y stuck at 0, which is uncovered when we apply the 8th test vector, which is 1, 0, 1, 1. So T is equal to 8 in this case. So you need to apply a subset of the possible inputs, which is smaller than the total set. But that subset is still kind of large. I mean, it's 8 bits in this case, but it's going to be much longer in a practical circuit. So if you have 16 inputs and you only need to apply 1/10 of the possible test vectors, so then in that case it's 2 to the power of 16 over 10, which is still a huge sequence of bits that you need to observe and compare to the original, to the correct output pattern in order to detect the presence or lack thereof a fault. Now, this is kind of very hard to do in hardware, because how can you compare 2 words that are 2 to the power of 16 long? When you do comparison in hardware, you usually do it using subtractors. And in this case, you don't actually need a 16-bit subtractor. You need a 2 to the power of 16-bit subtractor. That's huge. You need a 64,000-bit subtractor. This is huge, and it's also very slow. because if you examine the delay of adders, you will find that at best the delay of adders increases logarithmically with the number of input bits. And in this case, it's going to be a huge adder that occupies a very large area, probably an area that challenges the area of the circuit under test, and also it's going to dominate the critical path of your circuit. So this is not tenable, this is not practical. And what we need to do instead is find a way in which we observe the output sequence coming out of the circuit and just compress it basically into a smaller word, and that word should tell us if the circuit is functioning properly or not. And this is exactly what happens with this part of the circuit, the signature analyzer. So as you can see here, a signature analyzer looks kind of like a linear feedback shift register. You can see that there are similarities between these two circuits, but there are also differences. The first difference is that the signature analyzer does have an external input, and that external input happens to be the output of the circuit under test. A linear feedback shift register doesn't have an external input. It just generates a periodic sequence based on an initial seed. In this case, we do need an external input because that's what we are examining, the output from the circuit under test. The other difference is that you could have linear operations, XORs, between the registers of the shift register. So these four flip-flops do not, strictly speaking, form a shift register just because the input of this bit is not going to be the output of the preceding bit. It's going to be a linear combination of two bits. So this is certainly not something that can be described as a linear feedback shift register, although there are similarities. Now we're going to draw a new truth table. This is a little bit more confusing than the first truth table, so bear with me. What we have in the first column here is the cycle starting from the seed. So basically we have the same sequence as in the original truth table, with the seed being the 1000 sequence, and every cycle counting from then on is a clock signal that follows it. And so cycle number 8 here is going to be number 7 in this case, because the first cycle is counted as the seed. And so we're going to apply a number of cycles, and at the end, at the 16th cycle, what remains in the shift register is going to be called the signature. And so let me explain what that means. We have a number of columns here. Let's begin with the column for F. What does this column contain? This column contains the contents of this register, which I already said is not properly a shift register, but I'm going to refer to it as a shift register just because it's convenient. So this refers to the contents of this register. So the contents begin with 0001. And this is the seed. The seed is inserted by the designer or by the user when we start activating the test. And so this is the seed that this register contains. With the application of cycles, there is an output F coming out of the circuit under test. The output F is this sequence. So it's 0, 0, 0, 0, 1, 0, 1, 0, and so on. Now you take this output sequence and you feed it into the signature analyzer, taking this as the initial seed, and you apply a cycle. So that the output from this bit is 1, the first F we have is 0, XOR together they give us a 1 in the first register, and then you figure out the bit value of the other registers, and that's the contents of this register at the end of the second cycle. And you keep following this pattern with the output F applied in every cycle, and at the end what you have remaining in this register is called the signature. So at the end of 16 cycles, what you will have remaining in the register is 1000 if the circuit is functioning properly, because in that case the output will be the pattern F that you applied. So for the other columns in the truth table, the pattern that you apply to the signature analyzer is the pattern that will be generated for that fault. So this pattern for A stuck at 0. And again, you keep tracing the contents of the register for every cycle, and at the end of the 16 cycles, this is the signature that you end up with. So what's the point here? The point is that you have taken a sequence that is 2 to the power of m bits long. This is the output sequence. In this case, it's 16 bits that is produced out of the circuit under test. And you have compressed it into the remainder here, the remainder after the 16 cycles have passed. In this case, which shows the remainder to be 4 bits, which is m, but it doesn't have to be. So you compress it into n bits, where n is less than 2 to the power of m. So this allows you to observe a very short vector that gives you an idea of whether the circuit is working properly or not. Because as you can see, the signature that we have remaining at the end of the test, if the circuit is working properly, which is 1000, is different from the signature that we have remaining for any of the faults. In additionally, the signatures that you have for the different faults are different, which allows you not only to determine that the circuit has a fault, but perhaps also to determine which of the faults have occurred. Now, this sounds a little bit too good to be true, because it is. The fact that we have compressed the output means that we cannot actually distinguish all the faults that can occur, meaning that the signatures that remain in the signature analyzer might be identical for some faults. I mean, notice first of all that the number of faults we are considering here, which is 7 faults, is less than the total number of possible faults in this circuit, because this circuit has 10 nodes, meaning that it has 20 possible faults. Notice also that some of the faults will always have identical outputs, meaning, for example, the fault, if you go back to the original table, the fault F stuck at 0, for example, the fault X stuck at 1, as well as the fault F stuck at 1 will always have the same outputs, because in both cases the output of the circuit is going to be stuck to 1. And this means that even if you apply an exhaustive test, you will not be able to distinguish which of these 2 faults occurred. And so when you look at the signature, you will definitely not be able to tell which has occurred, because they will always have the same signatures. In fact, signature analyzers are even worse than that, because you could have circuits that have different faults that have different output patterns that yield the same signatures. So the design of signature analyzers is not an easy task. What you want to do is you want to choose the size of this signature analyzer, so that first it gives you a brief number, a brief signature that indicates whether the circuit is functioning properly or not, and what kind of fault has occurred. So it has to give you a meaningful signature. But also, because it's a compressed signature, it will give you some false information sometimes. So you don't want that to happen very often. So there's a trade-off here between brevity, or a small signature, and between the ability to distinguish which fault has occurred in the choice of the size of the signature analyzer.